All right. Hello, everyone, and welcome. We'll go ahead and get started today. Thank you for joining us for our webcast. This will be our last one of the spring before we take a little bit of a break. This is on bioretention design adaptations for a changing climate. So before we get started, just a couple of reminders and housekeeping items. We do have two quick poll questions at the beginning. Just go ahead and use the options. I think you all are kind of used to that by now. We will do questions and comments. You can put them either in the Q&A or in the chat. I will keep an eye on both. Q&A is probably a little bit easier if you want to use that feature. Those of you who are on just heard the little announcement. We are recording this session. So that means that a recording of today's webinar, along with a copy of the slides, will be available on our website in the archived events section, usually within a day or two. So keep an eye out for that. And then we do appreciate your feedback. I have a very short evaluation survey at the end, as always, 3 or 4 questions, less than a minute to fill out. Just lets us know that we're doing a good job. Another reminder, I think most of you on here know us by now, but if you are not already signed up as a member of the Chesapeake Stormwater Network, it is free to join. ChesapeakeStormwater.net/join just gets you access to our monthly Stormwater Scoop newsletter, where you can get the information on the latest webcasts, new fact sheets and resources, updates from the Bay program, as well as our BUBBA Awards, which we'll have coming up starting this fall. As I mentioned, this will be the last one for the spring, most likely. We do have 3 from earlier this spring. If you missed any of them, you can check those out in the archives right now. They are linked here if you want to grab this slide deck after the presentation when I get them up on the website and follow those, or you can go poke around yourself. We had 2 in a campus stormwater series, one from Morgan State University and one from UMBC, talking about the stormwater programs, opportunities, and challenges on college campuses. And then we had one on how many events do you need? So it was a data-informed approach to developing pollutant monitoring programs for your stormwater best management practices. All really great webcasts. I recommend them highly if you want to check those out or share them with your colleagues. And so I mentioned this will be the last one for the spring, but part of that is because we have a really exciting program coming up later this summer and into the fall. This is our Chesapeake Urban Stormwater Professionals Training Program. I've been teasing this for a couple of weeks now. We will have a full set of marketing materials ready for you guys in about 2 weeks, where we'll have all of the dates for the program, how to register, and how to sign up. We're really excited about this program, really focusing on young stormwater professionals, but really anybody that is kind of looking for a refresh. It's going to cover all of the basics in a really hopefully fun and flexible sort of way to sort of fit your needs as a professional. So keep an eye out for that. You can check it out on the Stormwater Scoop. We'll also be doing a bunch of outreach directly to probably a lot of you as well. So with that, I will go ahead and open up our poll questions. I'm going to launch them both at the same time, the way I usually do. So go ahead and fill those out so that we can learn a little bit about you. The first is just our standard, who are you representing today? We'd like to know who our audience is and where you're coming from. So what sector, sort of government, non-government, private sector, academia are you from? If none of those fit, I didn't put another option in the poll today, but you can just drop it in the chat. Always interested to know where you're coming from. The second question is sort of an informal version of one that we asked in our biennial stormwater professionals survey that we just wrapped up, in case any of you took that survey. But it's really just how climate change has impacted your bioretention so far. If you've seen an impact, these are some of the common answers that we get in terms of more routine maintenance, more severe maintenance needs where we're having to retrofit or replace some of our older bioretentions. Maybe there's an effect that we're seeing where we're not capturing as much water, or we haven't seen an impact yet. If none of these really fit, maybe you haven't seen an impact and you don't want to be prepared, I would recommend, maybe this isn't the webcast for you, but don't log off, but you can let us know in the chat as well. All right, we've got some good responses coming in. I'll go ahead and flip this around, share the results. So we've got a nice group of folks here today. Local governments strongly represented, about almost half of you, but all of the sectors represented, which is great. And then same as far as the impacts on the bioretention. I imagine some of the others might be in all of the above if you've got a lot of programs. Some might be not applicable if you don't have the BMPs on your own. But we're looking at more maintenance, more water bypassing, and some others. as well. So looking forward to this presentation today. We will cover some of what we can do about some of those issues. With that, I want to go ahead and introduce our speaker today. I'm really thrilled to have Dr. Matthew Jones here with us. He leads Hazen and Sawyer Stormwater Practice Group and offers national expertise on the full life cycle of stormwater control design, implementation, maintenance, and performance monitoring. His efforts include developing solutions with green infrastructure and other stormwater controls to address CSO reduction, water quality improvement, drainage relief, and climate resiliency. I had the pleasure of seeing a version of this presentation in the past, and thought it would be a really great addition for our webcast series. I'm excited to be able to bring it to you all today. So with that, I will step back. I'll hand it over to Matthew, and you can take it away.
Great. Thanks a lot, David. Pull up my screen, and yeah, really happy to be here today and share with you all on this topic. To start, really the focus of our discussion today is going to be on bioretention design adaptations for a changing climate. We'll go ahead and roll right into that. So first, I want to talk about, as we all know, green infrastructure has increased a lot in popularity over the years, become a lot more prevalent. It's worth noting that a lot of the focus in the presentation today is going to be on bioretention, but many of the things that we're talking about have some broad applicability to other types of green infrastructure that we're applying, particularly in the urban environment. So while we're seeing a lot of green infrastructure implementation for a variety of reasons, we also, and that's kind of the context of today's presentation, understand that storms are changing. And changing in a variety of ways, frequency of storms, intensities, durations, depths, all of those characteristics are things that we are seeing some changes in a lot of variability. So we increasingly were asking ourselves questions about, better understanding what are those changes and what implications does that have for the green infrastructure, particularly bioretention, that we're designing and implementing, maintaining, all of those things. So one way that we looked at that is really trying to understand how are storms changing. So we have a tool where we compared measured rainfall data to NOAA Atlas 14, kind of the standard for developing our design storms often. And it compared about 10 years of observed storms and said, okay, are these storms occurring at a greater frequency or a lower frequency than what Atlas 14 would project on average? This is especially helpful because in many cases, that Atlas 14 analysis can be somewhat dated. And I think we've often anecdotally anticipated that there are some changes. So those changes and this kind of analysis is obviously very location dependent. And I'm just showing one example here. Across the top are different durations of storm events. Down the side here are different recurrence intervals. The lighter box is how many storms we would expect on average. And then the darker box is how many were observed for this particular location. Now, you see some things that stand out here. One, we saw some relatively short duration, pretty large events, up to 100-year. Generally, our green infrastructure and bioretention, we don't reasonably expect that it's going to be doing much for that type of an event. But it's also notable and have kind of highlighted in the box here that where we see some of the greatest departures from those Atlas 14 averages are in the more frequent and also shorter events. So when we think about green infrastructure that's often sized for the water quality storm or around about an inch of rainfall, this gives some insight that perhaps we can have some impact, meaningful impact on these storms that, they're not causing widespread flooding necessarily, but they may be responsible for, localized complaints and localized issues. And again, we're seeing a lot of changes there. The other is when we look at historical rainfall, looking at our water quality depth, often the sizing of our green infrastructure. And we see variability there. When we look at, for this particular location, if we look at the 85th percentile, it's about a 1.3 inch depth, but it's worth noting that year over year, there is variability. In some locations, we see an awful lot of variability in that, both in terms of the percent of annual rainfall volume that's represented by that depth, as well as the frequency of those water quality storms. So that's looking at the past. But what about when we look at future climate conditions? So of course, we can use general circulation models to evaluate this and really look at all the interactions of the atmosphere, the oceans, land, surface, and ice on a global scale, and project things like temperature, precipitation, sea level rise, and then through a variety of downscaling efforts, kind of take that to a more locally relevant scale. One thing that's important to note is that those models tend to do a pretty good job projecting temperature trends over time. It's inherently harder to project the specific precipitation response. So something that you'll see, and this will be somewhat of a theme, is some variability in what those projections are. So one thing we can look at, and I apologize, the scale on this graph may make it a little difficult to read, but this is using the US Climate Resilience Toolkit. This happens to be for Washington, DC, looking at the annual days with greater than 1 inch of precipitation. That shouldn't be plural, sorry. And what you can see here, it's a bit hard, as I said, sometimes these models can be difficult to pin down specifics of storm changes, but you can see some indications here that as we look out over time through the rest of the century, some increase in the number of days with more than 1 inch of precipitation. So something that we would be focusing in our green infrastructure on. It's worth noting these red and blue lines, those are the medians for different climate scenarios. And then the bands here, which are notably wide, are the range of different model projections over time. So some signs of an increase, a lot of variability. We can also look at, one of the questions that we were wanting to answer is, not just understanding what are the implications for our typical green infrastructure performance, addressing water quality or CSO reduction, kind of a volume reduction for that water quality storm. But does green infrastructure potentially have a role in managing larger events? So to look at that, we use the SWIM climate adjustment tool to look at different projections, focusing on our 10-year, 24-hour storms, since that's a common level of service for stormwater conveyance. And what are the projected changes? So there's a range of scenarios here represented by the different lines, as well as different timeframes. For the context of this exercise, we looked at the far term time horizon, which I believe is the 2070 timeframe, and picked from those different scenarios what was the high estimate change and what was the low estimated change. When we look across the range of locations throughout the US, you can see what those current 10-year, 24-hour design storm events are, and then what the low adjustment and the high adjustment would be. One of the key takeaway, or a couple of key takeaways, one is that there's some variability, as you might expect. In fact, in some cases, there's a projection that that design storm may have a lower depth in the future. But it's also worth noting that when we think about, go back to our question about what is the role of green infrastructure or bioretention, that some of these adjustments are closer, the adjustments themselves are closer to our typical green infrastructure sizing criteria. So another key factor, and something that we're seeing a lot, is that priorities are changing. And that within that, I think in large part to changing storm characteristics and ongoing development, flooding and the ability to address stormwater conveyance needs seems to be growing in importance. This is at a recent conference, somewhat of an informal poll we did of the conference attendees. This was on a different topic having to do with stormwater master plan. But we asked folks in the audience, there are about 50 or so, well, what is your top priority for stormwater improvements? And it's notable that for more than half, flooding and drainage relief was their top priority. And this was from a group, largely folks in the Chesapeake Bay watershed. So it speaks to kind of that, and then I guess paired with that is important to note, how many priorities do you balance? And almost everybody, in fact, I think all but one person has to balance multiple of these objectives. So, flood and drainage relief and water quality and beyond. That speaks to, really benefit in understanding, how storms are changing and what are the implications of that. So when we look broadly at how storms are changing, we see an increased frequency of smaller storms contributing to nuisance flooding, and we tend to see incremental increases in 10-year storm depths. So back to the question that we were asking ourselves is, what is the role of green infrastructure in this? And two specific questions relate to that. Can green infrastructure mitigate incremental increases in storm depth associated with climate change? And can green infrastructure play a larger role in managing localized urban flooding? So if green infrastructure could play a valuable role here, that could have a lot of benefits. One of the challenges, kind of the typical approach for addressing stormwater conveyance limitations, is pipe upsizing. So this can be a very disruptive activity and a costly activity, especially in areas of existing development where you have a lot of utility conflicts and all. And while we didn't do a life cycle analysis per se, it's certainly reasonable to believe that when you add up the impacts, the material that's being removed, disposed of, manufactured, that this can be quite a disruptive activity. And it's important to note that that's still going to be part of the toolbox. But maybe I'm jumping too far ahead. But what we wanted to understand is if green infrastructure could play some role there, could provide a lot of benefit. Green infrastructure in this context, we're not expecting it to replace the role of piped conveyance infrastructure, but could it provide some added capacity such that upsizing could be delayed, or by managing some of the runoff from increased storm depths and intensities, could we negate the need to do that pipe upsizing? So that was really the fundamental question that we were asking. So to do that, we did some hydrologic routing through a typical curbside bioretention area. This was sized to manage runoff from a 1-inch storm. We assumed a soil infiltration rate of 1/2 inch per hour, both at the bioretention surface and into the underlying soil. We ran a 10-year, 24-hour NRCS hydrograph through that, a fairly common storm used for sizing pipe conveyance systems. We routed that flow through the bioretention, accounting for bypass and overflow, and we looked at existing and future conditions with and without green infrastructure. And the question that we were asking is that if the peak flow from the future condition with green infrastructure was less than the existing condition without green infrastructure, then that green infrastructure effectively mitigated the changes, projected changes in storm sizes. So we looked at a handful of bioretention modifications. So a basic bioretention with no internal overflow, that sort of thing. We looked at an internal overflow. So this could be a stone gabion, as is shown in the graphic here, that allows a perforator riser or an inlet distribution pipe, something that allows water, once it starts to pond up on the surface, to more quickly get down into that stone reservoir at the bottom. And notably, this is exchanging, as with some of these practices, exchanging some water quality treatment to increase your storage capacity. We looked at a controlled underdrain option. So this is taking that underdrain and rather than having it free flowing, putting some kind of a flow restriction on that underdrain. So that could be a cap with a drilled orifice, a weir wall, a valve, or even an automated valve. For the purposes of this exercise here, we sized that restriction so that it maximized storage within the bioretention for the 10-year event. And then the other scenario was an iceberg GI, which I'll come to a bit more in a minute, but this is generally to manage a 2-inch event instead of a 1-inch event. So as I noted, one of the things with some of these practices is they're acknowledging that there's going to be some trade-off. Even with our internal overflow, typically looking to have some surface storage that we're making sure is filtering through the bioretention soil media. But again, there is some trade-off with sending more water directly into the underlying soil. So we've got a series of slides that are going to follow a somewhat similar pattern. So across the top here, you can see what the sizing target is, if there's an internal overflow, a controlled underdrain, and what the storm is. And here's the hydrograph here. So this is the flow in CFS per acre. This is over time across that hydrograph. And you can see the different lines here without green infrastructure and with green infrastructure for the existing condition, and without and with for the future condition. And for this scenario, this is our standard bioretention, no design modifications. You can see that it does very little for our 10-year event. And what is essentially happening is that the surface capacity that we have available fills up very quickly. The amount of water that's moving into the underlying soil is slow, and so the capacity of the system is exceeded pretty early. And you can see that reflected here under our current setup with no green infrastructure. We're at 5.2 CFS per acre. The green infrastructure provides some incremental reduction there, but not enough to counteract those increases in storm size for our future climate condition. So what happens with that scenario? The capacity of the system is exceeded before the peak of the storm event. That marginal peak reduction we're seeing is attributed to infiltration into the bioretention soil. And the same thing happens under future conditions. So based on the question we were asking, the criteria we were set, this setup was not mitigating the effects of changing storms. So here we include the internal overflow. So you can see some difference here. We're better utilizing the storage of our system, but we still exhaust the storage capacity of that system before the peak of the storm arrives. So the overall result for the peak is the same, 7% increase from the existing under that future climate condition. So again, better capture, but we're not able, the capacity is exceeded and we're not able to mitigate those changing storms. So here we're layering those design modifications on. So we are including the internal overflow, which is an important element, but we're also tying in the controlled underdrain. And here you can really start to see noticeable reductions and what is happening is we're fully utilizing the storage capacity that we have available, but we're also releasing water before the peak of that storm arrives. So when that peak does arrive, we still have capacity in our bioretention and are able to regulate that flow. And here you can see under our current conditions, a substantial reduction just by adding the green infrastructure, and that does more than overcomes the future climate conditions. So an overall 35% reduction from the existing. So this does, we're regulating the flow throughout that storm, substantial peak reduction under both current and future conditions, and this does meet the criteria that we set for mitigating those impacts of changing storms. And then I mentioned another scenario you want to look at. It's essentially an upsized bioretention. Now that doesn't have to be an iceberg bioretention per se, but particularly in urban areas that may involve something where you have a shallow surface footprint and a larger subsurface footprint, hence the iceberg reference. So when we look at that scenario, keeping the internal overflow and the controlled underdrain, you can see even more that additional sizing really goes even further in addressing our peak flows and more than counteracting those future climate changes. So the last scenario that we looked at from this routing, so we're calling a gutted bioretention. Now, as a big green infrastructure enthusiast, this is somewhat horrifying, but the intent is kind of a responsive repurposing of bioretention to maximize storage and support drainage relief. So in some respects, it's forgoing the water quality benefit and removing those filtration and treatment elements and really doing what you can to maximize the storage within that same footprint. So it would include a controlled underdrain. It really becomes kind of a mini detention feature. But one thing that's worth noting here, maybe it's not all bad, is that this could be something that could be retrofitted near the end of a functional life of a bioretention area. So the kind of scenario where you have a bioretention that's been in operation for a long time, you're looking at replacing the soil media, maybe you've had fines migrate into the stone layer. So you're looking to remove that material anyways. If that coincides with noticing you have drainage issues in the area, kind of a repurposing of that to focus more on drainage relief and less on water quality. And when we route that scenario through, again, with that internal overflow and that controlled underdrain, the largest reduction yet of the scenarios that we looked at, 91% reduction for the existing. So that capacity, essentially using up all of that pore space that we have available, and then putting that controlled underdrain in at a tailored flow rate to optimize for that 10-year peak, really dramatic reduction in peak flows there. So looking across the different scenarios that we were evaluating, again, the basic bioretention did not do very much under existing or future conditions. Essentially, that capacity was exhausted pretty quickly. It's worth noting that from a water quality standpoint, which typically that's going to be, of course, a smaller storm, lower intensity, still a lot of great value there. Same with our internal overflow, including that element by itself didn't meet our drainage relief target here. But when we add in the controlled underdrain, when we increase the size of our green infrastructure, or if we go with that gutted bioretention configuration as a retrofit, all of those were able to have some substantial reductions on our peak flows. So back to our two questions that we posed: can green infrastructure mitigate incremental increases in storm depth associated with climate change, and can it play a larger role in managing localized urban flooding? The answer to both of those are yes, but with some important clarifiers and caveats. And I think generally we would characterize it that green infrastructure can be part of the toolbox, but its use and its benefit is going to be heavily dependent upon site specifics, and often paired with more conventional means of providing drainage relief. So some conclusions here. Changing storm characteristics may alter bioretention performance and desired function. That's something I didn't touch on a lot, but one of the things that may occur is with an increase in frequency of storm events, or an increase in those high intensity storm events, which is a relatively common projection, certainly throughout the Chesapeake Bay watershed and beyond. There are likely to be some long-term performance implications there. Things like our typical bioretention without any kind of internal overflow may capture less of that volume with those higher intensities. And then from a maintenance standpoint, it's reasonable to believe that more sediment and other things maybe flush into our bioretention systems with more frequency and require more maintenance as a result to address that. And I think from the poll that David did at the beginning of the meeting, perhaps some indications or some experience with that from the audience here. Simple green infrastructure where peak flow mitigation is not considered in the design is unlikely to have much impact on those peak flows in the context of broader stormwater conveyance in those larger storm events. Inclusion of internal overflows and controlled underdrains provides operational flexibility and could help with drainage issues. That's really a key point, particularly with the controlled underdrain. One of the real great aspects of that is that for most configurations where you would implement a controlled underdrain, it's something that could be readily retrofitted over time or adjusted over time. You know, for example, and I know there are a number of programs that are already using controlled underdrains in different capacities. But that can be as simple as having your underdrain pipe that goes into a threaded cap. Initially, you may keep that cap completely closed, really focusing on water quality and infiltration. By having that underdrain there in that capacity, you can gradually increase the size of that orifice over time as needed to tailor the capture of your bioretention to the storms that you're trying to manage. And that's especially important when we think about the variability in storm characteristics and how those change over time. Having that operational flexibility provides a lot of value. And of course, you can take it a step further by looking at automated controls and things of that nature that can look at what is the storm that's being projected and best tailor the release rate from that bioretention accordingly. It's worth noting in the context of this exercise, and this is an important point, this is looking at your typical NRCS design storms. Real storms don't necessarily match that. So you're going to see some different performance there when you look across a wide range of real storms. When we talk about the role of green infrastructure in mitigating drainage issues, the ability to site green infrastructure is a key element. I know a lot of folks have experience citing green infrastructure in urban areas. The exercise here was assuming that we can get all the flow to our bioretention, but we know that that's not always the case, and that may limit the role that green infrastructure can play in providing relief to the typical storm drainage network. But again, fits with that broader conclusion that it may be it should be part of the toolbox and considered, but it's certainly not going to be a silver bullet solution. And related to that, where we're seeing, I think, nationally, the most interest in implementing green infrastructure in this capacity for drainage relief is where you have highly constrained environments, or you have constraints on where you can upsize maybe a length of pipe, but you can't carry that all the way downstream. And something where green infrastructure with the design modifications we discussed here can help provide some of that detention to help facilitate addressing those issues. And then the last point, and perhaps the most important, is trying to be proactive in planning for future storm events, whether that's thinking about continue to focus on water quality with bioretention and how an increase in frequency or depth of that water quality storm may affect the performance of that over time, or thinking about how priorities may change over time, and whether a bioretention that in the near term is primarily focused on water quality improvement, but how might it in the future be adapted to provide some drainage relief function if that's expected to become of value later on. So again, wanted to thank you all for listening in today, and I think we've got plenty of time for any questions that folks may have.
Excellent. Thank you, Matthew. Really appreciate it. Great presentation. We do have a couple of questions coming in, so we can dive right into them. First from Carol, a question about the modeling analysis, wondering what the existing soils infiltration rate was that was used for the peak flow models.
Yeah, no, that's a great question. So we assumed an infiltration rate of a ½ inch per hour, both into the surface of the bioretention and into the underlying soil. And so the results are going to vary, obviously, with what assumption that you make there. Typically our design targets for our surface bioretention infiltration rates are of course higher than that. But I think when we've looked at systems over the long term, that's not altogether uncommon to have something in the neighborhood of a ½ inch per hour. So that's what we use for this analysis. And I guess the other thing I'll note there, we did look at some different infiltration rates. And as you might expect, that higher infiltration rate provides some better capture, but nowhere does it come close to the benefits of the internal overflow and the controlled underdrain in terms of overall volume management.
Great. We had a question from Russell asking if you are currently applying a scale factor for Atlas 14 rainfall depths to project future rainfall when designing for green stormwater infrastructure facilities.
Yeah, so that's a good question. We have tended to look at that, and it varies. I'd say in most cases we look at it as part of the design process to look at what those projections are. And then we kind of make some decisions. In some cases, we're able to go ahead. Typically, we look at what that is, and then we have a conversation with whoever we're designing the facility for to kind of lay out, okay, well, this is what the current standard is. This is what the future condition is projected to be. Typically, that would suggest some level of upsizing, and then making a decision on whether that considered to be cost effective or not. So we tend to look at that. One of the great things is that the tools to kind of evaluate that are increasingly accessible. There are a number of kind of web-based tools and all that provide some context for what those future changes might be. And that's another important point to make, that they provide context. Nothing gives an exact answer, and that's not a commentary on the state of climate models or anything else. It's really just the simple fact that by projecting future conditions, there's always going to be some level of uncertainty. But we tend to do that to look at that just to have a more informed design. Does it always result in upsizing the practice? Not necessarily, but we try to take a look at it anyways.
Yeah, I think that's a great question, and actually one that I wanted to kind of build off of a little bit, since we do have in the Chesapeake Bay here, a tool now that Rand and Marisa put together, where you can look at these change factors for the entire Chesapeake Bay watershed under these different climate scenarios and sort of get a sense of what that difference is going to be, and we're still sort of working on how to apply those. But I was sort of wondering, kind of along with that, you sort of stacked some of these design adaptations on each other for this analysis to sort of show the incremental, increases. And I was wondering if you did any analysis that sort of looked at, sort of a standard bioretention design, but it was upsized for future climate conditions to sort of see what that benefit by itself would be.
Yeah, no, that's a great question, David. And that's something I didn't include it in this particular slide deck. But one of the things that we've looked at before is changing things like your surface storage. So like thinking about, as part of the initial design, if say, instead of like 6 or 9 inches of surface ponding, if you were to increase that to a foot or 18 inches. And so that's something that could be done physically by, putting a lip around the Atlas structure or something like that. So, but we want to think about, there's some performance trade-offs, right? Your drawdown time is going to be longer. You're going to have more surface ponding. So some of those things are less desirable. And but thinking through in the design process, kind of those range of options. So you've at least trying to avoid the scenario where you implement something that just meets the current standard, and then 10 years down the road, someone's thinking, oh, well, it'd be nice if we could hold a little bit more water, but we can't because of X, Y, and Z. Trying to think about kind of what are those kind of modifications that you can make down the road, even if you're not implementing them to start.
Yeah, and I think that adaptability actually leads in nicely to another question that we have from Jill, just asking if you're aware of any case studies of folks using the automated smart controls for bioretention basins. We've sort of seen some folks starting to adopt those smart controls, particularly on pond structures up here, and wondering if you've sort of seen the same in bioretentions.
Yeah, I'm not familiar with any bioretention examples in detail. I feel like I've heard some discussion about using it in bioretention, and I've certainly familiar. In fact, we implemented a system, automated valve system for a pond retrofit. I'm not familiar with the details of any case studies with bioretention, but I think it may be something that's being looked at currently, and certainly something I think that there's some value to look at. One of the trade-offs there, I think, is, or I presume, has to do with the cost effectiveness of, with a pond, you're getting typically you're managing a much larger volume. So the cost of the automated control in relation to that volume managed may be more favorable than a smaller system, but I think the cost of those kinds of systems and those controls are going down. So it's something I would expect that we may see more of in the future.
Then we had another question, wondering if you looked just at precipitation in this analysis, or if you happen to look at, either in this study or in any of your other work, at impacts from sea level rise or even saltwater intrusion on some of these impacts as well. It's certainly an issue in our lower lying regions of the Bay, and I imagine in North Carolina too.
Yeah, so this that I'm showing here was focused on precipitation. Sea level rise is a challenge. As you all know, with for bioretention, really all of our green infrastructure, having some groundwater separation is important, and then we have the potential to lose that over time. So that is a factor. It also, I think, somewhat fits in with the thinking about the future adaptability. So that may be, for example, a scenario where, under current conditions, your soil infiltration capacity and your groundwater separation may suggest that you don't need an underdrain, but perhaps under future conditions, having the option of having an underdrain may facilitate some of the drainage from the system. So we didn't look at specifically at sea level rise in this particular context, but that is important. It's also, I guess worth making that connection. We were talking earlier, David, about the question that you brought up about kind of thinking about that future adaptability. And that thought process is very similar to seawall design and that sort of thing, where you are thinking about, okay, well, what is the sea level rise projection? But thinking about, okay, how could I increase the height of that wall in the future if I need to be more protective and that sort of thing. That same general kind of thought process applies here.
Great. I'll throw one more in if other folks don't have any more. But I just wanted to ask too, with the topic of maintenance sort of came up, and the potential increase in maintenance to bioretentions and other green infrastructure practices under changing climate. For folks that maybe aren't as familiar with some of these design adaptations and things like that, I was wondering if you could talk a little bit about the potential either benefits or trade-offs around maintenance for controlled underdrains and internal overflows and things like that.
Yeah, no, that's an excellent question. Something I probably should have touched on some. So a few things. So for the internal overflow and the controlled underdrains, so I'll start with some benefits and challenges, and I tend to prefer to end on good news. But so one of the benefits from a long-term maintenance standpoint is directly relevant to what we're talking about here: the ability to get water into the system. So as I'm sure many folks have experienced, one of the vulnerabilities of bioretention is surface clog, or really any of our green infrastructure is surface clogging, and that seeing some surface clogging combined with increased storm intensities creates a scenario where you're going to have more bypass from your system because water can't get through. So that's where the internal overflow comes in. One of the negatives with that is that you also have the potential to send more fines, mulch, and debris down directly into your underdrain or into your subsurface layer of your system, which then becomes harder to access and maintain that. So in a number of cases where you have that internal overflow, it's paired with some other type of treatment mechanism. So that may be as simple as kind of a stone covering of that kind of graded inlet to help capture some of that debris and keep it on the surface. Or it may be, a drop-in screen into that drain that's capturing some of that and keeping it from getting down to the bottom of the system. So that, is certainly a consideration there. I guess the other thing, I don't know if I got into detail on this, but typically with that internal overflow, you're raising it above the surface of the bioretention. So it may sit at like 3 inches, a 3-inch height. So, some of the material that you're capturing and dropping out is presumably below that depth. And also making sure that you're not getting direct bypass, that you're still getting some treatment on the surface. With the controlled underdrain, one of the, and especially if those things are paired together, one of the concerns could be if you've got a small orifice and you've got a way for solids to get down directly into your underdrain, that it could clog the underdrain. So that's where, there are different design configurations to address that. I know we've implemented some at a larger scale in urban areas where we'll have kind of a manhole with a weir wall and that flow restriction in the weir wall. So you've got, more readily able to access it for maintenance and that sort of thing. But those are some of the key considerations there from a maintenance standpoint.
Great, thanks. Yeah, and definitely the kind of thing where I think as we start to implement more of these design adaptations in the field, we'll really want to be paying attention to, and hopefully funding some studies to look at performance over time too, to see how these maintenance obstacles kind of stack up, and whether we lose some of those benefits and sort of what the trade-offs are as they go along and we face
absolutely
hard to avoid.
Yeah, absolutely. And I thought of one other thing, and that's with the controlled underdrains, ignoring the kind of drainage improvement side of things, but that's another thing with the controlled underdrain. And I may have mentioned this earlier from a maintenance standpoint, if you have, whether you have an internal overflow or not, but if you have clogging at the bottom of your stone layer, there's no easy way to address that, right? But if you've got an underdrain in there, even if it's capped to start, you can increase that release rate so that your bioretention is not, kind of sitting saturated with water. You've got some mechanism for water to get out of that facility, just in the context of kind of future maintenance and kind of changing operations in response to different levels of maintenance.
Great. Well, seeing no other questions, I think it's time for us to go ahead and wrap up. I'll just remind folks, I did put a link to our evaluation survey in the chat. If you all wouldn't mind clicking on that on your way out today and filling that out for me, I would really appreciate it. Thank you so much, Matthew, for joining us. Really interesting stuff, and looking forward to sort of seeing some of these techniques get implemented around the watershed and beyond.
Great. Thanks a lot, David, and thank you all for participating today.
All right. Thanks, everybody. Good luck getting back into the swing of things after the long weekend.